Hi everyone, Jeremiah here, and today we're going to talk about breadth first search. So we've taken a look at some of the problems we can run into when we're doing search, and we've taken a look at what happens if we use the very naive approach. So what we're going to do this time is we're going to use a variant of a breadth first traversal called a breadth first search and include a duplicate check so that we don't run into the problems with toggles and other types of duplication. The main difference between a traversal and a search is that a search has a goal check, whereas in a breadth first traversal, we're just going to go through all of the options until we exhaust them. In a breadth first search, every time we consider a node, we're going to check and see if it's the goal. And if it is the goal, we're going to stop. So let's consider an example. Let's look at a map like the one we have here, where we want to plan a path between A and D. First of all, we're going to need a queue to store the nodes on. Once we have that queue, we need to store the starting point, the initial problem state in the queue. And then while the queue is not empty, the first step is we're going to pull the first node off of the queue and consider all of its possible children. In this case, the possible children are F, B, and E. The next step is we would check to see if any of these are duplicates, but in this case we haven't visited anything yet, so none of these are duplicates. So we're going to add them to the queue. Once we've done that, we're finished with this node and we restart the loop. Next we'll pull E off of the queue. E is not the goal, so we will look at all of its children. Its children are A and D. However, we've already visited A, so we will only add D to the queue. And then we're done with E. Next, we pull B off of the queue. It is not the goal, so we consider all of its children, which are A and C. But again, A is a duplicate, so we will add only C to the queue. Next, we'll pull F from the queue, but F has no non-duplicate children. Finally, we pull D from the queue, and this is our goal, so we're going to trace back. We got to D from E, we got to E from A, and so our path is AED. So there's a few properties of searches that we're going to see again and again, and so we're going to define these words now. It's important that you understand these words in context, but not necessarily that you memorize them. First, we would say that breadth first search is a systematic search, and that means that it processes nodes in order. In the case of a breadth first search, because it's using a straight, standard FIFO queue, that order is first in, first out, or first come, first serve. We would also say that breadth first search is an uninformed search, meaning that it uses no special knowledge to guide the search. Imagine if you stepped into a room and it were pitch black, and you were told to find an object in that room. You would be executing an uninformed search. We also say that breadth first search is optimal in terms of steps. But the word optimal is an interesting word because it means the best. And best is subjective. I think the best ice cream is chocolate with chocolate chips and chocolate chunks. You might think something different. You would be wrong, but you might think that. But in all seriousness, the key point here is that optimality is a word that must be qualified to make it an objective measurement. In this case, we're going to qualify it by saying that it must be optimal in terms of the number of steps required to solve the problem. In other words, it will find the best solution in that it will find the solution that requires the fewest number of steps. Breadth first search is also a complete search, which means that it promises to find a solution if one exists. And finally, it is an exhaustive search because it will also find a solution if it exists in a finite state space. Now, all of these words seem pretty similar, and there is a relationship between them. An optimal search promises to find the best solution for some definition of best, which means that, by default, all optimal searches are also complete, because they find a solution, they find the best solution. Likewise, all complete algorithms are also exhaustive, because they promise to find a solution as long as one exists, which means that, even in a finite state space, they will also find a solution. So let's take a look at the 8 puzzle example again. If we start with this problem state, we have two options. We could move the 8 over, or we could move the 7 down. If we move the 8 over, we're going to get this problem state. Because it's not a duplicate, we'll add it to the queue. If we move the 7 down, we'll get this problem state, which is also not a duplicate, so it will also be added to the queue. And then we're done with the starting state. Then we pull the first element off of the queue, and we consider its possible successors. If we move the 6 over, we'll get this problem state, which is also not a duplicate, and so we'll add it to the queue. If we move the 8 over, however, this problem state is a duplicate, so we will not add it to the queue. Finally, if we move the 1 down, we get this problem state, which is also not a duplicate, so we'll add it to the queue. If we pull the next element out of the queue, we have 3 options again. If we move the 1 over, we get this problem state, which is not a duplicate and will be added to the queue. If we move the 3 down, we'll get this problem state, which is also not a duplicate and will be added to the queue. And if we move the 7 up, we'll get this problem state, which is a duplicate again of the first state, so we will not add this one to the queue, and so on and so forth. Let's step back for a moment and consider the difference between a breadth-first traversal and a breadth-first search. Remember that the key difference is that a search has a goal check. So what we have here is the algorithm for a breadth-first search, which adds only a single line to take it from a traversal to a search. In this particular example, we've left out the duplicate check, which we'll add in the next step. So just like a traversal, we start with a root node and we enqueue that root. And then while that queue is not empty, we pull the first element off of the queue, and this is where they diverge. We have a goal check immediately after taking the first element off of the queue. If it's the goal, we're done. The algorithm is over. If it is not the goal, then for each child of this node, we're going to enqueue that child. Wash, rinse, repeat. If we don't find the solution by the end, in this case we return null to indicate that we did not find a solution. So let's take it one step further and consider how we might use a breadth-first search for problem solving rather than just exploring a tree. So what we've done is we've taken the code for a breadth-first search of a tree, and we're going to modify it by adding a few lines to turn it into a breadth-first search for problem solving. In this case, our for loop goes through each valid operator of the current state, and we need to add a step. We need to apply the operator to the current problem state to derive a successor state. We also need to add a duplicate check. If this is a duplicate, we're going to skip over it. Only if it is not a duplicate, if we have not visited this problem state, should we add it to the queue. We also need a way of checking what we have visited and what we have not. And there is no free lunch here. We must keep track of each and every problem state we have ever visited if we want to perform a complete and accurate duplicate check. In this case, we're going to use a map data structure, an associative array that associates a problem state with a tree node, which we're going to call the planner node. So to recap, we start with a queue and a visited map, and we'll call the queue the open list. And we must wrap a tree node around the problem state and put it in the queue. We must also indicate that we have visited this node by adding it to the visited map. While the queue is not empty, we will pull the first element off, and we will do a goal check to see if it's the goal. If it is the goal, we're done and we complete the algorithm. Otherwise, for each valid operator at the current problem state, we're going to apply that operator to derive a successor state. We're going to check to see if it's a duplicate, and if it is not, if it's a new problem state, we're going to wrap that problem state in a tree node. We're going to keep track of how we got there by setting its parent, and we're also going to mark that we have visited this problem state. And finally, we must queue that node up. Now, we also mentioned a tree node or planner node structure. We usually refer to the tree nodes in a problem-solving algorithm as planner nodes to distinguish them from other types of nodes like graph nodes or other things of this type. There are 2 key components that must be a part of any planner node data structure. First, it must contain the problem state itself. The problem state that this tree node, this planner node represents, must be contained within the planner node. And we also must keep track of how we got to this planner node. What is the traceback path so that we can reconstruct the steps we've taken to get to this point. Taking it one step further, we can also create a variant of this for a pre-constructed graph. This is particularly effective with path planning, but also works for other types of problems. We're not going to add a lot of code here. We're mostly going to make modifications. The biggest difference is that instead of using a problem state, we're going to be using a search node, which is wrapped around a problem state from a graph that we've constructed already. Instead of operators, we're going to go through the edges of that vertex. And deriving our successors is only a matter of following the edge to its endpoint. In the planner node, that means that we will be tracking vertices instead of problem states. There are a few important optimizations we should consider anytime we construct a search like this. These are already built into the pseudocode on the previous slides, but it's worth mentioning them because these types of problems occur frequently. The first is that you should always try to generate nodes after you have done a duplicate check. And nodes in this case refers to the planner nodes or tree nodes. The reason for this is fairly simple. If you create a planner node and then do the duplicate check, you have to delete it. You have to get rid of that memory. And allocating and freeing memory over and over again will cause memory fragmentation and other problems that usually result in cache misses. We'll also get much better results if we use a data structure built for random access, like a map or a dictionary type, to keep track of where we have visited. This will lead to much faster duplicate checks and allows us to search just a single data structure instead of multiple data structures. The last point, while not built into the pseudocode before, is a very important practical consideration when working with game engines or similar systems. And that is that we need to be able to split the search across frames if we're to effectively integrate a search into a system that must respond in real time. This eases the workload off of a single frame and allows the AI to share the CPU with rendering and other subsystems. And these optimizations in general will reduce our memory footprint by reducing fragmentation, reducing cache misses, and improving speed. So breadth-first search is the first algorithm we've seen that can practically solve problems, whereas before, the problems quickly grew too big for us to actually solve. With a breadth-first search, because we integrate a duplicate check, it becomes plausible. However, there are problems with a breadth-first search. The first is that it is optimal only in terms of the number of steps. So in our example here, even though the middle path is the shortest, with a distance of 9, because of the number of steps required to reach the solution, our agent will actually take the path AED. In addition, breadth-first search requires a great deal of memory and a great deal of CPU time to execute. So think about how we might improve upon that, and we'll address that in the next video.